Okay, so today we're going to be starting chapter 1. We're starting at the very beginning of where the book's going to take off, solving simple equations. So the number one thing that I see with students is they either want to solve one side of the equation, like solve an expression, or when they have variables on both sides and they're trying to solve an equation, they tend to get mixed up on some of the rules. So this whole section is designed to kind of be about how do we clarify what the rules are when the variable's on one side or if it's on both sides, and what are the generalized steps in solving any equation. These are all very basic equations that we're going to be doing. We're not doing anything complex like anything with quadratics or exponentials, just basic linear equations with nothing fancy in them. Now there's a lot of ways that we can do equation work. This is one of them. I like to teach a very general method so that you understand if I do this every single time, I will get there, and then as exceptions come along, I'll introduce different ways to do those. So let's go ahead and get started on the first one. So this is going to be chapter 1, section 1, so 1.1, and it's solving simple equations. Okay, and you will notice that this solving simple equations isn't one step or two step or anything like that. It's just a generalized, let's do a couple of them. So the first thing, we're going to say variables can be combined either on the same side and we call variables on the same side, we're just going to call them generic like terms. Or on opposite sides. We're going to call these split terms. Okay, so we've got two different types. We have like terms or split terms. Now, split terms are a type of like terms. They're just a subset. The terms are not like because they're on one side of the equation, they're on both sides of the equation, so we call them split. The other thing that we need to know how to do is, what is a variable? One of the biggest things that I get students that are concerned about is they're like, oh, a variable is a letter. So you're going to see one of the questions that we're going to do today, we're going to have a letter that isn't a variable because it's a known value. So a variable is anything that either varies internally, we don't know what it is just yet. If I write down a generic equation that we haven't solved, let's say 2x plus 1 equals 3x minus 5, all divided by 6. You just looked at that, you haven't solved it yet. If I told you x equaled 3, you did, okay, cool, I'll believe you. If I said, actually, no, I solved this, x equals 2, okay, cool, I'll believe you. It varies in our head because we haven't yet solved for it. This is a variable because we haven't figured it out. Or let's maybe say this actually has a known value, we just don't know it. Let's say the value is the amount of time it takes to fall. So I want to know how long it takes to fall, and I'm jumping off a cliff. So cliff, jump, time. And I want to know how long it takes to fall off the edge of the cliff. So in this case, my t value, whatever equation I come up with, varies depending on the situation. How high is the cliff? Is the cliff 50 feet? Is it 100 feet? Is the cliff 50 feet, but there's actually depression in the bottom? Is there water? Has the water been raised? So it varies depending on the scenario. So those are two different types of variables that you might run into. Either we don't know what they are, but the idea is that t could have been many different things. Could have been 2 seconds, 5 seconds, 10 seconds, we don't know, but they all sound good. So as long as we know what a variable is, like terms and split terms are the two topics that we're going to cover. The first one is going to be like terms. And like terms are on the same side of the equation. And they can be combined using PEMDAS, or just regular order of operations. we have variables on the same side of the equation, and they're combined using PEMDAS. So our first example, I'm going to give you two examples. One that's very, very straightforward, and one that leads us into what split terms might look like and what sort of logic that we're going to have to follow in order to solve those. So our first one is 2x minus x equals 5. And our second one is going to be 3 times 4x plus 5x equals 54. Okay, so now with this, the first one, what I always like to do, this isn't a required thing, I like to draw a line right down the equal sign. What I've noticed is that a lot of students who tend to get mixed and matched over, is it the same side, is it opposite sides, am I combining terms or am I inverting them? This helps keep things balanced. It gives me a left side to simplify and a right side to simplify. So the first thing I'm going to do is I'm going to identify where are my x values, or where are my variable terms. The variable terms that I have are both on the left side of the equation, which means that I can use PEMDAS to simplify this. So I have 2x minus x. What does that mean? Well, the best way I can describe it is if you have 2 apples and I have 1 apple, how many apples do we have together? I'd say, well, 3 apples, duh. Well, let's look at this mathematically. What is this saying? If I have 2 apples, you have 2 of these things, and I have 1 of these things. Sometimes I write a number 1, sometimes I don't. And that adds up to 3 of these things. Is it 3 apples squared? No, and that makes very good sense because I'm not squaring it, it's just 3 apples. 2 apples, 1 apple makes 3 apples. Okay, cool. So when I look at this one, I have 2x minus x. I have 2 apples and I'm taking away apple. Now I understand that there's going to be an invisible 1 right there. So I'm looking at the same style problem. I have 2 apples minus an apple, and a common mistake that I see students give is they'll say, well, 2 apples minus apple is just 2, because I took away the apple, right? I think you see through this one. I'm not taking away the apple, I'm taking away 1 apple, and I had 2 right here. So it's not 2 apples minus apple is 2, it's 2 apple minus 1 apple. I'm looking at the coefficients. I'm saying 2 minus 1 is going to give me 1 apple. So when I say 2x minus x, I get 1x. So I get 1 x equals 5. Okay, perfect. Now, you might write the 1, you might not. No big deal. I'm going to ghost it out right here because if you wrote it, awesome. If not, no big deal. I'm going to box up my answer because that's it. X equals 5. Like I said, very, very straightforward. So the like terms, they're on the same side. If I look at number 2, again, I'm going to draw my line right down the middle, and I'm going to identify left side and right side. Where are my variables? Are they both on the left? Are they both on the right? Are they split? Well, in this case, again, they're both on the left-hand side. So I'm going to go through and I'm going to say, hey, using PEMDAS, what can I simplify? So the first thing is I notice in PEMDAS, parentheses comes first. So I'm going to go inside the parentheses and say 4x plus 5x, does that simplify? Yeah, just like my apple problem. 4x plus 5x is going to give us 9x, and the parentheses don't go anywhere. 3 equals 54. I didn't touch the 54, didn't touch the 3, all I did was combine what's in the middle. Okay. So the next thing I'm going to go say, okay, is there anything else in the parentheses that I can do? No. Any exponents? No. What about multiplication and division? Yeah. I see there's a 3 and there's a set of parentheses right after it, which implies multiplication. Now if there's more than one term in there, there's distribution. But that 3 right abutted up against the parentheses means that I'm multiplying 3 times everything inside. The everything inside is 9x. So 3 times 9x gives me 27x. Okay? And now, that's pretty much as far as the like terms are going to take us, and we're going to start moving into what we're going to do when we have split terms, or how are we going to be solving an equation. So when I look at the 27x, again, nothing I can simplify here, nothing I can simplify here. I'm going to have to solve the equation, which we know 27 times x is going to be, let's go ahead and undo that by doing division, divide by 27, and we'll get x equals 2. And now a lot of you, I might have lost you in that last step, because you're like, okay, that makes sense, this makes sense, what did we do right here? And now this is how we start solving an equation. So let's go ahead and jump into, first off, what is a split term? And we'll see how we solve these guys. So split terms are on opposite sides of the equation. And they can be combined using inverse operations. Okay, so split terms, they're on opposite sides of the equation, and they can be combined by using inverse operations to cancel one of them out. So let's take a look at an example. I have 5a minus 1 equals a plus 15. Okay, now with this one, the first thing that I'm going to do, again, I'm going to draw my line right in the middle. That'll separate my left and my right hand side. And I can look at the left hand side and say 5a minus 1. Can I use PEMDAS? Can I combine anything using parentheses, exponents, multiplication, division, addition, subtraction? No. I see I have a subtraction sign, but that's an a term, that's a number. They're not like terms, so I can't combine them. Over here I have an a and a 15. Again, they're not like terms, so I can't combine them. So I'm going to say, okay, I'm going to have to cancel one of these terms out because I've identified that I have an a on the left and I have an a on the right. I need to get rid of one of them. Now if I look really closely on this 5a, the 5 is going to be a positive 5a, which means in order to think about that as how I get rid of it, positive 5a can be thought of as plus 5a, or add 5a. And we know the opposite of addition is subtraction. So I would subtract 5a. Or, what I can do over here, is I see this a has an understood 1. In fact, that understood 1 is a positive 1, which means it's positive 1a or plus 1a. And again, the opposite of addition is subtraction. So I could subtract 1a. At this point, it's a matter of choice. Do I want to do that, or do I want to do this? Doesn't matter which one. Most of us are going to get rid of the 1a, or the number that's farther to the left on the number line, because it tends to leave most of our other coefficients as positive numbers. So I'm going to go ahead and I'm going to subtract the 1a, which means I subtract 1a from the left and from the right hand side. Because let's think about it this way. With my line, what I've done in red here is I've done something to one side of the equation. I have to stay balanced. If I take $1 away from everybody on this side of the classroom, it's not fair to them. It's definitely not fair to these guys. So I'd have to go ahead and take $1 away from everybody over here. If I give this side over here, let's say a popsicle or a donut, I'd have to also give this side over here a popsicle or a donut in order to keep things balanced. So this line tells us if I subtract 1a from the left or from the right, I need to also do it to the left. Right now it's not balanced. And again, the reason why I draw the line is, let's say, for example, I had another number off to the side. Let's say there's 1a over here and I have another 2a on the end. I see a lot of students oftentimes go ahead and subtract 1a, and look what they did. Is that balanced? No, I did it twice to the right hand side. That's super not balanced. So we don't want to do that. The line helps us keep it balanced. Hey, I did this over here. Now let's go do that same thing over here. And now what happens when we invert an operation? It cancels out. So that a cancels out because I inverted it. And that leaves us with a new line. So I'm going to say, there we go, new line. That's gone. The 15 I didn't touch. So I have a positive 15. I didn't touch the minus 1, but I did have 5a minus 1a. So just like my apple scenario from earlier, 5a minus 1a gives me 4a. There you go. So now I've got that. Now that both my variables are on the left-hand side, actually my only variables on the left-hand side, now I can go through and I can continue inverting other operations in order to cancel out everything that's not an a value. Now, if I combine everything using PEMDAS, what's the easiest way to think of an inversion of PEMDAS? Do it backwards. So we're going to quite literally invert it. So we're going to use, let's write PEMDAS backwards. P-E-M-D-A-S. SADMAP. Inverse of PEMDAS. So when I'm solving the equation, I'm going to start with the addition and the subtraction. Because a lot of you might say, well, do I get rid of the 4 or the -1 first? Start by doing the inverse. Now there's lots of ways to work these equations. There's other ways that may be faster in certain scenarios. But again, I like to keep things very, very simple in the beginning, so you can always get to the answer following the same set of steps. Later on, you will find shortcuts and tricks on how to do things faster. But in the beginning, let's just keep things very, very simple. I invert it by going in the opposite direction. So I'm going to look at my A term. Yep, do I have anything added or subtracted? I do have a -1. So what is the inverse that would cancel out subtraction? Addition. So if I subtract 1, I add 1. And now I see I did something on the left, so I gotta come over here and do that same something on the right. But if I invert a term, that term cancels out. So that leaves me with my next line. I didn't touch the 4a. That's canceled. But now the 15 has a +1. That's going to give me a 16. And if I continue using this inverse, I have got rid of everything that's added or subtracted. Now I'm going to move to multiplication and division. I see that I have a 4a. Now, what operation is that? Well, when I see two things side by side, just like earlier, that implies multiplication. Another way that I like to look at it is, if you didn't notice, what operation do you see between those? Well, if you stare really, really, really closely, did you notice there was a dot there the entire time? Oh, yeah, never mind, you're just paying attention now. So you're like, oh, hold on, I see that dot. So if you ever don't see anything, remember to like zoom in and be like, oh, yeah, that must be a dot there. It's just too small to see without having zoomed in. Even if you're doing this in person, just zoom in with your eyes. Okay, there's a dot. So I see the dot, I know the dot means multiplication and division, so I'm gonna go ahead and do the opposite. So the opposite of multiplication is division. I'm gonna divide both sides by 4. So that it is to the left, I'll also do it to the right. Now again, what happens when I invert an operation? The 4 has been inverted, so I cancel it out. But does the 16, is that inverted? No, I'm just dividing 16 by 4. So that'll leave me with just my a over here on my left, and 16 divided by 4 is 4. And there we go. Now, you might want one more example, just in case. And where was my example? 3g plus 2, 2g minus 1. Okay, so let's take a look at this one. I have 3g plus 2 equals 2g minus 1. So I'm going to, first thing I'm going to do, I'm going to draw my line right down the middle. And I'm going to say, hey, let me look at the left and look at the right and see, can I use PEMDAS to simplify? So if I look inside the parentheses, I can't simplify. A g and a 2 are not like. If I look over here, the g and the 1 are not like. So I can't simplify anything in the parentheses. There's no exponents. But when I get to multiplication and division, I see that this 3 is right up against that set of parentheses. So if I look really, really, really closely, I see that there's a dot right there. It means multiplication. And with the parenthesis, that means I'm multiplying 3 times everything on the inside, or what we call distribution. So 3 gets multiplied by g, and the 2, everything inside gets multiplied by 3. So 3 times g is going to give us a 3g. And 3 times 2 is going to give us a 6. Everything got multiplied. Same thing's going on over here. If you look really, really, really closely, that 2 in that parenthesis, you'll notice there's a small little dot that was there the entire time. So that 2 is getting multiplied times everything on the inside. So we distribute a 2, which means the g gets multiplied by 2, and the -1 gets multiplied by 2. So I get that. And now at this point, I have simplified both the left and the right. Now that they're simplified, what I can do is I can start inverting them. Well, pause. I haven't finished
getting all my variables to one side. Right now I have a g on the left and a g on the right. So I've got to either get rid of this g by noticing that it's a positive 3 by subtracting 3g, or getting rid of this 2g. Noticing it's positive, I would subtract 2g. Again, you have two choices. It doesn't matter which one you do. I'm always going to pick the one farther to the left of the number line because it's going to leave us with more positive coefficients, and that scares students a lot less. So I'm going to subtract the 2g, which means I come over here and I do the same thing. Subtract 2g. Anytime I invert something, it cancels out. Okay. So at this point, the g has fully canceled out on the right, but I had 3g on the left. I took away 2g, so I know I pay attention to the coefficients. 3 minus 2 is going to give me a 1g, of which I don't necessarily need to write the 1, so I'm going to ghost it out just in case you wrote it. Awesome, you can keep it. If not, you don't need to. Not necessary. I didn't touch the 6. I didn't touch the negative 2. So at this stage, what I can do is, again, I'm going to see, is there anything else I can invert? Well, my g's are all on the left, so let's follow that inverse order of operations. P, E, M, B, A, S. Let's start with addition and subtraction. Yep, I got an addition sign right here. I'm going to invert it by subtracting the 6. So let's subtract a 6 from both sides. Anytime I invert something, it cancels out. That goes away. And so all that I have left over here is my g, with or without the 1, it doesn't matter, equals negative 2 minus negative 6 is going to give us negative 8. Bingo. Now notice, every time I get to an answer, what am I doing? Boxing up my answer. Perfect. So I think we got the idea of what happens when my variables are on the same side versus when they're on opposite sides. And really, the process is very much the same. Simplify what you can on the left or on the right individually. Then once they're fully simplified, start moving things over by using the inverse. So if you're moving from one side, if you want to get rid of things on one side of the equation, inverse. If you're just combining things on one side and it doesn't matter what's going on the other side, just follow calculus. So let's go ahead and cover a few other examples. These are other types of inverse operations you might run into. They're just generic little tidbits. So if I look at, let's see, number 5, 6, and 7. So 5, 6, and 7. Number 5 is x minus 3 equals negative 5. Number 6 is 0.9 equals y plus 2.8. And number 6 is pi x equals negative 2 pi. Okay, so when looking through these, they're going to give us a couple different style inverse operations. Number 5, really easy. My variable's on my left. I follow the inverse order of operations. Again, blue is dying there. Please excuse my dear Aunt Sally. Start with addition subtraction, work my way over. I have a minus 3, so I'm going to go ahead and add 3 to both sides. That's inverted, so it cancels out. Okay, so I have an x equals negative 5 plus 3 is going to give me a negative 2. Okay, pretty comfortable with that. If I look at number 6, again, I'm going to draw my line right to the middle. My variable's on the right. Following this in reverse order, I see that there is something being added. I have a plus 2.8. So in order to get rid of plus 2.8, I subtract 2.8. Subtract 2.8. Inverted, so it cancels out. Okay, so all I have left over here is my y, and then I have a negative 1.9. Now, when I box this up, this irks some people where they're like, pause, everything we've done so far, x equals something, g equals something, a equals something, the variable's always on the left. Why did I box it up when the variable's on the right? The variable's isolated. As long as the variable is isolated, I know what y equals. Y equals negative 1.9. I don't need to flip it around. Now, sometimes, like in geometry, you'll want it to fit in a certain way. So let's say I want the y on the left. I'll have to take an additional step to say y equals negative 1.9 and move it over. But That'll be in a geometry thing, but either one of these is fine. Just stick with that. Now, number 7, this freaks a lot of people out because they're like, pause, I see 3 letters. Therefore, I must have 3 variables. Therefore, how do I solve something with 3 variables? Not as hard as that, because a variable, if we remember, is something that varies that we don't know yet. So if I asked you before we solved this, what was y? I don't know. If I asked you before we solved this, what was x? I don't know. If I asked any of these before you solved it, would you know? No. But what is x? I don't know. What is pi? Immediately you should think, well, 3.14, right? Well, okay, cool. So you know what that is. So is pi a variable? No, it's not. And is it actually 3.14? No, it keeps going. It's 3.14159265. And it keeps going. But you rounded it to 3.14. I'm going to do one extra. I'm going to round it to 3. Well, 1/4 does round down to 3, right? Okay. So let's say, for example, you looked at this question, and let's say you thought it, instead of saying pi, you wrote out the number of pi. 3. We're ignoring the 0.14. So it's 3x equals negative 2 times 3. Okay, I know how to solve that, because how do I get rid of the 3? I see that little dot right there, and I know that with that little dot, I would divide this side by 3 to cancel it out. I would divide that side by 3 as well, and I would get x equals, see, negative 2 times 3 is 6, divided by 3 is negative 2. That makes sense, right? Let's solve the same thing. How do I get rid of the number in front of x when it was multiplied? Through division. So how do I get rid of the number in front of x when it's multiplied? Through division. We just said that. Let's go ahead, draw our line, and I'm going to go ahead and say that number in front of x is pi. So I'm going to divide by pi. And anytime I invert something, it cancels out. So I have an x equals, pause, look over here. I have a times pi divided by pi. Are multiplication and division opposites? So over here on the right, they also cancel out, and we're left with just this. So you knew how to do that all along. Pi is just a number, so treat it like a number. We just don't write it like a traditional number like 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. That is its own number, pi. Let's do a few more, and then that should be good. So 8, 9, and 10. Okay. So for number 8, I have g squared equals 169. Number 9, I have the square root of r equals 8. And for number 10, I have this new thing. I have a cube root of b equals negative 3. Now this is really intimidating for students because they're like, what? But you already know how to solve this. So let's walk you through how you already know how to solve this. So the first thing is we need to identify some opposites. So the first thing, we discussed what the inverse of this means. The opposite of addition is what? Subtraction. So those are inverse operations. We know the opposite of multiplication is division. Those are inverse operations. So what I'm implying here is there has to be an opposite of a power. Well, let's think about the most basic power. This is a square power. What's the only other term in math at this point that you know has the word square in it? Square root. Exactly. So square roots and square powers are opposites. They cancel each other out. So if I have a power, all I do is I get the root, and that will be my third set of inverse operations. So again, if I have a g to the power of 2, that's like saying g squared. How do I get rid of a square in the power? Well, I put a square in the root. Okay, so I have a square power. I square root, and guess what? They go bloop. They both cancel out. I'm left with just a g. But if I square root the left, I have to square root the right. Now, what is the square root? The square root, remember, is any number that's multiplied by itself that many times. How many times? Square power is 2, so square root must also be 2. I need a number multiplied by itself twice, so number times number will give me 169. What number is that? 13. Pause. There's another number that when multiplied by itself gives me 169. Do you know it? Think about that. What number when multiplied by itself gives me 169? A lot of you might say immediately like 1. 1 times 1 is 1. You're like, no, 1 times 169. It's got to be the same number. That number times itself 2 times. So you might be tempted to say, well, how about, let's see, that's 84.5 is half that? No, because that's adding. 12 by 12 is 144, 14 by 14 is 196. I'm lost. How about this? Negative 13. Negative times a negative is a positive. 13 times 13 is 169. So negative 13 times negative 13 is positive 169. So you actually have 2 different answers when you use a square root artificially. I put in the square root, therefore I have 2 answers. So that being said, when it's already in there, I'm gonna have 2 answers because it's already there. But if I look at number 9, I have a square root. Pause. We know the opposite of a square power is a square root. So what's the opposite of a square root? Exactly. A square power. Now what that's going to do is that's going to cancel out both those, and I'm left with an r. Square power, this is easy. 8 squared means 8 times 8. 8 times 8 is 64. Not positive and negative because I'm just saying 8 times 8. Positive times a positive is not a negative. So they're only going to have one answer. And lastly, this is the weird thing that you probably freaked out about, but I think you might have already figured out how to solve this. I have a little 3 in the root. Now, pause. What did we say the opposite of a square power was? A square root. So what number must I not be writing in that root symbol that is there? Let's take a look at some of the other examples. If I have a number like x, that's a variable. What number do we never write in front of it? 1. What symbol do we not write in front of that? Well, it's a positive 1. What exponent do we not write? 1. So when I have a square root, I must not be writing a number. And I know a square root and a square power deals with a 2. So what number, when I have a square root, am I not writing? Well, it's the number 2. So square roots and square powers, because there's an implied 2 and that's a 2. This must mean this is a cube root. What power would undo a cube root? A cube power. Bingo. So I'm going to raise this side and this side to the 3rd power. And that's going to say, I have b equals, well, negative 3 cubed. That means I have negative 3 times negative 3 times negative 3. I have 3 of them. So first off, a negative 3 times a negative 3 is a positive 9. Negative makes positive. 3 by 3 makes 9. So negative 3 by negative 3 makes positive 9. The positive 9 times that 3rd negative 3, positive negative makes a negative. 9 times 3 gives me 27. And there we go. So that should really sum up like the beginning portions of like what solving simple equations are for today. We'll have more for you on the next one.